Hello, my name is Amir Mackey and I welcome you to Softstuf Philadelphia. This is our disturbance monitoring lab and we call this the home of the Bainbridge simulator. And what we are here assembled to talk to you about today is a wonderful project that we're doing with Con Edison under a smart grant from the Department of Energy. And what we have done basically is built smart sensors. These are little clothespin-like devices that we take and we just basically clip onto a wire like this, and in doing so we have digitized old analog infrastructure, and we take the other side of this cable on RJ45, which everybody's familiar with, and we plug it into a computer, and now we have digital information from these smart sensors available on the network and anyone can look at them. We did this basically to take old legacy infrastructure and make it look like brand new infrastructure. And what we have here, the home of the Bainbridge simulator, this is the Bainbridge simulator, and what we did is it's a substation simulator simulating both old legacy infrastructure with new digital infrastructure. The team members are John Walsh, who is going to explain to us the substation simulator and the power system simulator, Frank Rothweiler, who is going to play a fault into the system and he's not going to tell us what the fault is, and then George Samati, who will capture the data that came from these sensors. These sensors are inside these panels monitoring everything in this simulator. So I'll go ahead and turn it over to John. John, would you please?
Thank you, Amir. Here we have a power system simulator, and the power system simulator permits us to apply signals to relays, to test them, to stress them, to see how they operate. This gives us the necessary combination of currents and voltages to apply those signals. In these two panels here, the first panel is our relay panel. It's made up of electromechanical relays on 2 feeders and a microprocessor relay on a 3rd feeder. On the bottom of the panel here we have 3 lockout relays, 1 for each feeder, and the bottom handles with the white monitoring lights are our breakers. Here we have a control panel with the control handles for each of those breakers that allows us to open and close the breaker. And you can see all the indications here are red, indicating the breakers are closed. At this time we don't have any current flowing through the feeders, so all of our amp meters are reading 0. In the back of this panel we have the sensors to collect the data should an event occur.
Frank, would you please play us a fault? Don't tell us again what the fault is into the simulator, and then George will see if our smart sensors captured any of that data, and of course John before that will explain to us what happened on the simulator when you play that fault.
Okay.
And hopefully the story that John will give us and the story that George will give us will be a perfect match.
Okay. Thank you, Amir. I'm going to play my mystery fault file into the power system simulator, and we will have our fault file time tagged with a GPS clock to better than 1 millisecond. So I will start the software. The power system simulator is running, injecting current into the substation simulator.
Now if I were an operator in the substation, I would know that an event took place, because first of all I'd be in the control room and I would see my breakers go green, indicating that they opened. I would come out to my relay panel and see that on this lockout relay I have a red indication indicating that this relay operated. I would also see that I have loss of monitoring on my 2 breakers here, telling me that the breakers didn't in fact operate from a protective relay operation. That would be all the information I would have at this time. I don't know what kind of a fault it is, what time it occurred, any of that information. Amir?
Thank you, John. So now what we need is from George to tell us if he captured any files.
So right now you're looking at the Wavin software. There is no file right now, but there is a blinking right here. It's telling us that we have files captured by Wavin. So if I come here and click on refresh, oh, you see that we have 2 files here. And Amir, could you please come and explain about these 2 files?
It'd be a pleasure, sir. Okay, so we grabbed 2 files. I see the first file has a TIS extension and is colored dark, and the second one has an SOE extension. So this is my sequence of event file, and this is my trip information file. So let's go ahead and open our trip information file and look at what we'd see. Now, if I was an analysis engineer, this is what I would want to look at. First thing I would see is that these are my channels, phase A, B, and C, and the neutral. And right here are my control circuit channels. This is the lockout relay, this is breaker 1 trip coil, breaker 2 trip coil. George, would you please mark these and amplify them a little bit for me? Okay, yes, and just click on the up arrow. So as a fault analysis engineer, this is what I would want to see. One more time, please. Wonderful. So now you can unmark them so we can see them in their original posture. So now I clearly see that I have a phase A to neutral fault. Frank, did you play a phase A to neutral fault?
Yes, sir, that's correct.
John, does that agree with the information that you saw from the indicators on?
It agrees with the information that I observed at the relays panel.
Wonderful. So you can see the difference by old infrastructure. All you have is a light. Here you have the full waveform trace. I can look at my timing to see the fault duration. I see where the lockout relay open, trip. I see where the trip coils on breaker 1 and breaker 2 went. So clearly, this information makes legacy infrastructure look like a brand new digital equipment and allows us to extend the life of our existing equipment. So George, what I want to do finally is to just show some of the capabilities of this software that we provided for this project. So if you just hold the right arrow key and play, we will start with the pre-fault area, looking at 1 amp secondary value, and as you see, we moved into the fault area, and the rotating vectors are your A and neutral, and we are at about 8 amps secondary on the fault. Here's the neutral, and then when we come out of the fault, you see that the currents completely disappear. So we now have a complete picture of what actually happened. Now, if you're not a fault analysis engineer, you wouldn't want to look at squiggly lines like this. You would want some clear textual-like summary. So if we hit escape and we look at what we call the sequence of events, this is what would be transmitted to operators. Please open this file for me, George. And right there, I clearly see this is the event. It's a phase A to neutral event. The lockout relay opened and breakers 1 and 2. The lockout relay tripped and breakers 1 and 2 opened. This gives me the precise time that this happened, as Frank said, accurate to better than 1 millisecond. And then I can get the duration, so here's my breaker timing, and I can get the fault currents that happened on all of them. This is the system that we have built for Con Edison under the Smart Grid Demonstration Project grant from the Department of Energy. Thank you for watching.